In Chapter 7, we spent some time talking about principal energy levels, sublevels, orbitals, and then the electrons that ultimately go into the orbitals. We're going to take that information now and put that into the this part of Chapter 8, the first part of Chapter 8, periodic properties of the elements. Sections 8.1 and 8.2 if you want to read them for your own background knowledge. But we're going to jump right into sections 8.3 and 8.4, which focus on electron configurations. Electron configurations refer to the arrangement of electrons in an atom. The larger the atom, the more organization you need. The Aufbau principle states that electrons fill up sublevels in order of increasing energy. So the lower energy sublevels fill up first. Now you may have seen this figure before, and I'm going to show you how the electrons fill up. They fill the lowest sublevel up first, which would be 1s. Next would come 2s, followed by 2p, 3s. After 3s fills up, the atom's larger, more electrons, 3p, 4s. After 3p and 4s fill up, 3d, 4p, 5s. Continue on. After 5s, 4d fills up, 5p, 6s. Continuing on, 4f, 5d, 6p, 7s. And then if that atom is large enough, 5f, 6d, 7p, ending with the newly discovered or created elements that were named a few years ago. Okay. Now you may have seen this before. I'm going to show you a couple ways to write electron configurations. Okay, so the arrows refer to how the electrons fill up the sublevels. Now what we want to remember is that the sublevels, regardless of which principal energy level they're in, have a maximum amount of electrons that they can hold. An individual orbital, regardless of what the orbital is, can only fit 2 electrons at most, but the sublevels max out at different numbers. Okay, an S sublevel only maxes out with 2 electrons because it has 1 orbital. A P sublevel maxes out with 6 electrons. A D sublevel maxes out with 10 electrons, and an F sublevel maxes out with 14 electrons. Okay, that's due to the number of orbitals and the fact that at most 2 electrons can fill up an individual orbital. Sublevels have a maximum amount of electrons. I just had that drawing here, okay, with the sublevels and the red arrows showing the order. And I wrote that out here across the board the same way. 1s fills up first, followed by 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, and so on. Okay, the superscripts represent the maximum electrons per sublevel. Now you can have lower than that, okay, but S will not exceed 2 electrons, a P sublevel will not exceed 6, a D sublevel will not exceed 10, and an F sublevel will not exceed 14. Orbital diagrams are good to show how the electrons fill up the sublevels, but they're good for small atoms, okay? When you get to an element, having a lot of electrons, okay, this way is not feasible because you're going to have this really long, diagram, just like having a really long electron configuration as well. You see, this would be representative of the electron configuration for barium with 62 electrons. Okay, we're going to learn a shorter way, but before we go and do that shorter way, let's look at a small atom and let's look at what its electron configuration would be. Carbon has 6 electrons. The first sublevel that fills up first is 1s. Okay, 1s2. Okay, 2 electrons, 2 out of the 6 go into the 1s sublevel. That accounts for 4 more. Okay? 2s will take 2 more of those 6 electrons. Then we have 2 more remaining. Those 2 additional ones go into the 2p sublevel. Okay? So the electrons fill up each available orbital first before doubling up with another electron. That's Hund's rule. So those 2 remaining electrons, okay, they don't pair up right away. They want to have lower energy, so they spread out, okay, and they would fill up each individual orbital first before they would double up. Okay? Let's say that we had fluorine, okay? And look at the orbital diagram for fluorine. I'm just going to erase Hund's rule down here. Let's look at fluorine. Has 9 electrons. If we were to look at the orbital diagram for fluorine, okay, I'm going to keep the same orbital designations here. 1s2, 2s2. Okay, that's 4 of the 9. 5, 6, 7, 8, 9. Okay, so they fill up each individual orbital singly, and then they double up afterwards. Now, what would the respective electron configurations be? Okay, carbon, we have 2 electrons in the 1s sublevel. So 1s2, 2s2, 2p2. 2, 4, 6 electrons. We go to fluorine. 1s2, 2s2, 2p5. Okay, so our 2p sublevel is not maxed out, and that's fine, okay, because we don't have enough electrons, okay? That's not the element that we're writing the electron configuration for. So here are the electron configurations for carbon and for fluorine, okay? Carbon symbol C, fluorine symbols F. Well, what do we do when we get to larger atoms? We can make use of the periodic table because there's certain characteristics about it that we can use to our advantage to help us write electron configurations for larger atoms. You may have been introduced to this way in Chem 110, maybe not, but I'm going to show you how to write electron configurations for any element. We can use the periodic table to help us write electron configurations for an element. The larger atoms have longer electron configurations. You have more electrons, you have more sublevels, and more principal energy levels to accommodate those electrons that are part of that atom. We're going to learn a shorthand way to write electron configurations using the symbol of the preceding noble gas. Now recall that the noble gases are in group 8A. So the noble gases have 8 valence electrons. Oops, hold on. Okay, except for helium, which has only 2. But the noble gases have complete outermost sublevels, so they don't react with anything. Makes them very stable. Okay, so the noble gas symbol in brackets, okay, in square brackets, will account for the core electrons. So we're going to be using the noble gas symbol in brackets, and then we will need to write out all the other sublevels up to and containing the element in question. But before we actually do examples, I want you to take a periodic table and refer to figure 8.7 in the textbook. And I want you to mark off that periodic table with certain blocks, okay? So figure 8.7 of your textbook, okay, looks like this, okay? You have certain groups of the periodic table that are color-coded, all right? So I'm going to show you a chart that I have, which is the same. It's just easier for me to hold up a piece of paper than the whole book, okay? So go onto Canvas and print out for yourself another periodic table and mark it up, okay? Take, 4 different color crayons or markers or pens or whatever, okay? Groups 1A and 2A They are your S block, okay? Groups 3A to 8A are your P block, with the exception of helium, okay? So your representative elements, which are your group A elements, end in either an S block or they end in a P block. Your group B elements, your transition metals, they are your D block elements, okay? So go and mark those off with a different color, okay? Or you can circle them and then color them in later. Yes, you can refer to figure 8-7, but if you do it, on the paper, it helps you to remember it better. And then the lanthanides and actinides down here at the bottom, they are your F block. Okay, so make those designations there. Now, I also wrote that over here. Groups 1A and 2A, they're your S sublevels. Groups 3A to 8A are your P sublevels, except helium. Your transition metals, your B groups, are your D sublevels, and your lanthanides and actinides are your F sublevels, okay? So what I have written here is what I was saying to designate here. Now let me show you something real fast, okay? When you look at this periodic table, S maxes out with 2 electrons. S1, S2. P sublevels max out with 6 electrons. 1, 2, 3, 4, 5, 6. D sublevels max out with 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the F sublevels max out with 14 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. See how it all fits nice and neat into the periodic table? It's a chemist's best friend. Okay. We're going to take this periodic table, okay, with our blocks marked on it, and the fact that the noble gas preceding the element in question will represent the core electrons, we're going to do some examples now of writing electron configurations. Let's look at the following elements and write the electron configurations for these elements using the abbreviated method, abbreviated notation. Okay? So you can refer to figure 8-7, or you can refer to your periodic table if you have it color-coded. Let me just note too that you see how I have written here 1s, 2s, 3s. It's written also in your textbook too. But this represents the principal energy level with each sublevel. So the first principal energy level, okay, S sublevel, 2s, 3s, 4s, 5s, 6s, 7s. Remember, the P sublevel starts in the second principal energy level, 2p, 3p, 4p, 5p, 6p. Okay. The D sublevel starts in the third principal energy level, 3d, 4d, 5d, 6d, and the F sublevel starts in the fourth principal energy level, 4f, 5f. Okay. Magnesium. Magnesium, atomic number 12, okay, neutral magnesium has 12 electrons. Now, if we wrote out the longhand way, we would have 1s2, 2s2, 2p6, 3s2, because that's the order that the sublevels fill up in. But let's do the abbreviated way. What is the noble gas that precedes magnesium? If you look on your periodic table, okay, this is the one that I gave out in class. All right, we find magnesium, okay, and the noble gas that precedes it, comes before, would be neon. So neon would account for 10 of the 12 electrons, neon core, okay, and then we would have 3s2. So this symbol accounts for 10 electrons, which would account for these individual sublevels here, okay, and then 3s2. So right here, that would be your abbreviated configuration. Let's do a larger atom, scantium. Okay, a transition metal. Scantium, atomic number 21. Scantium, I'm pointing at the right thing, trying to read backwards. Yes, scantium, okay? 21 electrons, all right? So if we write the long method out, or the long abbreviation, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1, 2, 4, 10, 12, 18, 20, 21. It gets long, okay? So let's write the shorthand way. I am shown both ways because maybe you learned it the longhand way in 110 and maybe you didn't learn the shorthand way. So eventually we're just going to skip the longhand way and go right to the shorthand way. But if you look at scantium, the noble gas that precedes it is argon. Okay, remember noble gases, column 8A, group 8A, all right? You're looking here, okay? So argon core accounts for 18 electrons. That would account for all of these right here, okay? All of these right here are accounted for when you write that argon symbol in brackets. So that's 18 electrons. Okay, 4s2, 3d1. All right, let me go back here. All right, here's argon. Argon. Let me go back. Let me use this one because it's color-coded. Okay. Argon right here and scantium right here. So argon accounts for all of the electrons up to 18. Then you need to account for the remaining 3. So we have 4s2, 3d1. Arsenic has 33 electrons. Let's go right to the shorthand way. Arsenic. It used to be used as an embalming material, but because it would preserve tissues for a long amount of time, but it also was used to poison people, so they stopped using it as an embalming material. So arsenic, atomic number 33. Okay, arsenic right there. So the noble gas that precedes arsenic, okay, would be argon. Okay. So then we follow along. All right. Here's argon. 4s2, 3d10, 4p, 1, 2, 3. We'll end in 4p3. Okay, do we have our 33 electrons? 18 plus 2 plus 10 plus 3, 20, 33. Now that is much easier to write out, much more simplistic than writing all of those individual sublevels. Okay? Let's do some larger atoms, larger than arsenic. Zirconium. Iodine. 53. Let's do gold. Okay. Let's do these ones. find the noble gas that precedes the element in question and then follow along with the sublevels up to and including that element. Zirconium has 40 electrons. The element that precedes, the noble gas that precedes zirconium is krypton. That accounts for 36 of the 40 electrons. You don't need to write this here. I'm just showing you that accounts for 36 of the 40 electrons. So you have krypton right here, okay? And then you have zirconium right there. So you now need to account for 5s2, 4d2. And you may wonder, why does 5s fill up before 4d? Isn't 5s a higher principal energy level than 4d? Yes, but this 4s sublevel is lower in energy than the larger 4d sublevel. So they fill up in order of increasing energy. So yes, the principal energy level designation is higher, but the actual energy of the sublevel is lower. Okay, that's why you have 4s fill up before 3d and 5s fills up before 4d and so forth. There's our 40 electrons, okay, accounted for. All right, let's go to iodine. Atomic number 53, iodine right here. Okay, iodine. And the noble gas that precedes iodine, again, happens to be krypton. Now you may say, why don't you write xenon? Well, xenon comes after iodine. It has to be the one that comes before. Xenon has one more electron than iodine, so we cannot use xenon notation for the core electrons. Krypton. So again, 36 electrons here, okay? We need to account for 53. So let's go along, okay? We have krypton, 36, go down, 5s2, 4d10, 5p, 1, 2, 3, 4, 5. Okay, 36, 38, 48, 53 electrons. Okay, and that would be the electron configuration. Let's go to platinum. Okay, platinum is a very expensive metal. Okay, it's used in jewelry because it has a characteristic that it self-polishes. It's more dense than gold, so it feels heavier on the person wearing it. But platinum is also used in manufacture of catalytic converters in automobiles to help speed up the breakdown of the emissions. Okay, to speed up that process so that the larger molecules, which are more hazardous, are reduced to molecules that are not as hazardous. Okay, so to speed up that process, you have platinum that's part of the catalytic converter. It's an expensive part of an automobile to replace. Well, let's write its electron configuration. So platinum, 78 electrons. Okay, the noble gas that precedes platinum would be xenon. So xenon accounts for 54 of the 78 electrons. Okay, so here's platinum, PT. The noble gas that comes before it is xenon. Now we need to account for all of the sublevels that come between xenon core and the platinum. So now we have 6s2, but then, whoa, we have the lanthanides and actinides sandwiched in here. We need to account for that sublevel. And then platinum will end with a D sublevel, but we can't forget the fact that we now have an F sublevel as part of this configuration. So xenon core, 6s2, 4f14, 5d8. Okay, platinum is the 8th one over in the D sublevel. Okay, it ends in 5d8. Now, if you omitted the 4F14, let's say you did that, you would have 54 plus 2, which would be 56. Then you would have 8 more. That would only give you 64. And make sure. Yeah. Okay. You would be down 14 electrons, okay? So if you had 54 plus 2 plus 8, okay, that would give you the 64. You would need to account for those 14 to give you the 78. Okay, so don't forget that when you are looking at elements over here, okay, the transition metals that are in period 6 and 7, okay, that you need to account for the lanthanides and actinides as part of that configuration. And even if you're doing the representative elements that are down here, like tellurium and lead, bismuth, okay, and the new ones that have been named as well, which aren't showing on the periodic table I'm holding up here, but yeah, like tennessine and oganesson, the new ones that are named, okay, they're not written on this chart here, but you need to account for the fact that you have the lanthanides and actinide configuration to include in there. Okay. So this covers pretty much all of the elements in the periodic table for writing their electron configuration, except for a few that do not follow the rules. They are called the anomalies, and we have a few of them. We have some elements that do not follow the rules, anomalies, okay? Certain elements that are in the D and F blocks do not follow the standard filling up of sublevels. And you can see in your textbook, page 350 gives information about that. I'm just going to discuss a few of them. They fill up the sublevels to maintain the lowest energy, so they don't follow the standard rules. Two prime examples are chromium and copper. Okay, they're both in the 3D block. Chromium has 24 electrons. You would expect that the configuration would be argon core 4s2 3d4 to account for the 24 electrons. But no, that doesn't happen. What happens is that the 4s sublevel half fills and the 3d sublevel half fills, so that you have a stable configuration. It doesn't follow the rules of how you would expect it to. Chromium does that along with manganese, which is right, with molybdenum, which is right underneath it. And the other elements that are in that same column there. So chromium, molybdenum, tungsten, seaborgium, they follow where the S sublevel fills up half and then the D sublevel fills up half. Copper is another example, 29 electrons. You would expect that it would fill argon core 4s2 3d9. But in actuality, that 3d sublevel takes one of those electrons that would go into 4s to make the 3d sublevel max out instead. So you have argon core 4s1 3d10. And copper does that along with silver and gold, which are directly underneath there. So you can refer to page 350 of the text and see some other examples. The F subblocks, the F sublevels, the F blocks, they do similar things too. They sometimes fill up the D sublevel first and then fill up the F sublevel. They do some crazy things there, those D and F electrons. Hey, this concludes electron configurations, and we will continue on with more periodic properties in the subsequent videos.